So as Sridhar mentioned, my background is primarily in the design of signal processing communications, and more recently, machine learning systems in hardware. And by hardware, I mean integrated circuits, embedded platforms, and so on and so forth. And so when we try to implement these complex networks, a problem that we all run into is the issue of complexity. And precision requirements of these networks is the first step. It is the most powerful variable that we can play with, that we can optimize in order to reduce both the computational complexity as well as the storage complexity. And so the talk today is going to focus on this very fundamental question that is in front of us. I have a deep network. It's implemented in floating point. It's giving me the state-of-the-art accuracy in floating point, but floating point is too expensive. I want to find methods to reduce that complexity, storage as well as computational. And the question in front of me is what exactly is the precision requirements for the activations, the weights, and during training, the activation gradients, the weight gradients, and the weight accumulator, right? So all of those are tensors that consume a lot of computational resources. So in this line of work, one of the attributes of our work that we try to preserve and try to enhance is to answer this question with guarantees, that is giving theoretical guarantees, analyzing using analysis methods more than simulation or empirical methods. So this is the theme of this talk, and I'll illustrate some of the theoretical concepts and their impact in answering this particular question. So I want to acknowledge three of my graduate students who have contributed to the work I'll be discussing: Sharbel Sakar, Sujan Gonagondla, and Hassan Dibuk. So moving on to the next slide, I want to begin by pointing out the efficiency challenges in deep learning systems. And again, this is something you all know quite well, that to get high accuracy, we tend to go for more complex networks. And the complexity appears, the graph on the left, if I may use a laser pointer, you can see that there is as the accuracy increases, you need to have more operations per decision, as well as the storage requirements also start to increase. And so the challenge then becomes, how do we map it onto modern day architectures? These architectures are invariably von Neumann architectures, right? And von Neumann architecture has been around since 1945. And we've been using it very successfully for so long. Such architectures suffer from something called the memory wall problem, that says that the cost of actually getting data from memory onto the processor, whether it is an on-chip SRAM, whether it is an off-chip DRAM or flash, the energy costs are orders of magnitude higher in just data transfer, data movement. So the sort of the holy grail in all of this architecture world is to find ways to minimize model complexity, maximize sort of storage resources in hardware, and then find ways to actually prevent or reduce the number of data accesses as possible. So this is the memory wall problem that we face. And this problem, though it has been around for ages, and there are lots of papers written on addressing memory hierarchy, building better memory hierarchies, this memory wall problem has been aggravated today with the advent of machine learning and the advent of AI, right? So the efficiency challenge is what drives us. And so in our group, and I think a lot of us in the architecture and circuit community ask this question, we want to design systems, we want to design machines that can learn, but we want to operate them at the limits of accuracy, robustness, and energy efficiency. We want to know what those limits are. I mean, that those limits are also not known. We want to know what those limits are, design machines that can operate at those limits, and we want to do all of this providing guarantees. And this is one of the big problems with today's deep networks. It is very, very difficult to give guarantees on almost anything. You know, it is a challenge to actually provide theoretical guarantees. So in our group, I just want to point out, just to give you a flavor of how do we look at the world around us and what research vectors, activities we engage in. Ours is what I call as a full stack method or a full stack approach to efficient machine design, energy efficient, latency efficient, accurate machine design. And the starting point there is always starting with a low complexity algorithm, figuring out ways using algorithmic methods, theoretical methods to minimize the complexity of the algorithms that we want to design. And in fact, precision is a big first step in that direction, precision minimization, and then mapping those onto hardware, dedicated architectures, in-memory architectures. And so we have in our group circuit design activities. So we build chips, we actually try out those theory ideas in practice, go into the lab, take measurements and report the results. So there's a lot of work in designing, in mapping those algorithms into practical architectures. And underlying all of our work is this fundamental Shannon-inspired model of computation that our group has been advocating for many, many years. This model of computation cuts across the compute stack, and that is its strength. So it gives us certain principles and guidelines in when we do algorithm optimization, architecture, or circuit design. And this is a model of computation that strives to preserve the information content in the data as it is processed in software or in hardware. And of course, number of applications up there. So each of these buckets is a talk on its own. You know, there's a lot of activity, a lot of results, and a lot of conclusions that we can talk about. Today, I'll focus on the issue of designing low complexity algorithms, in particular, reducing the precision requirements of deep nets. And we'll begin with just setting the stage. Lots of hardware being produced as we speak. These are a bit dated, but they all have one thing in common. They're implementing deep nets and fixed point. And a big question that arises in all of these works is, how did you select 16 bits, 8 bits, 4 bits? How do you know this is the right precision for the class of networks that need to be implemented? And so in our group, we have tried to address these two questions. One, what are the minimum precision requirements? And to obtain those analytically, right? So paper pencil, I would say, predictive or prescriptive methods to find the minimum precision requirements. And a number of publications have been listed here that you're welcome to take a look at. So I thought for this particular talk, this is a sort of a big picture outline of what I'll be discussing. So I'm just taking one example network, VGGNet. And if we go inside the network, we all know, this is all well known, that the heart of the computational kernel is a dot product. So you have, actually it's a matrix vector product, which is an ensemble of dot products. You get quantized, you want quantized weights, quantized inputs, generating a quantized output. You pass it through batch norm, ReLU, get to the next layer, right? So that's the sort of the basic kernel, and then a number of those kernels are connected together to get a network. And in the network, again, we want to be able to ask, questions like, what is the mismatch between the fixed point network accuracy versus the floating point network accuracy? And for the dot product, we want to be able to say, what are the minimum precision requirements that I can assign to the output, to the two inputs, sort of the activation and waits, so that at the network level, the delta between the two accuracies, the floating point accuracy and the fixed point accuracy, that delta is within a certain delta. Okay, so this is the big picture view, and so the outline will be the first part of the talk. We'll focus on a dot product kernel. It's a very concrete kernel. Hopefully, it will give us an anchoring of our thinking when it comes to accuracy. So we'll ask the question, what is the minimum output precision requirements of a dot product? We'll assume the inputs, activation and wait inputs, they are already assigned some precision. Now, what is the output precision requirement? And then we'll ask the reverse question, what is the input precision requirements of a DNN for weights and activations, maybe for gradients, weight and activation gradients, so that the network accuracy is preserved. And finally, we want to take those two learnings from 1 and 2 and sort of an advanced topic. This is to find out the precision limits of in-memory architectures. And some of you may have heard about in-memory architectures. These are a relatively new addition to the portfolio of DNN accelerators that have been proposed. The jury is still out as to how in-memory architectures fit in the big picture, in the scheme of things, but they do present very unique and quite amazing energy delay product gains over digital architectures. And that's why there's a lot of interest today in such architectures. So let's start with the first one, the first topic, which is minimum precision requirements of dot product. This is output precision requirements. And so essentially we are asking, what is this BY that I need to assign to meet a local metric? So here I'm working at a dot product level. And you might ask, why are we so anxious about or so interested in output precision? Well, it turns out that the output precision affects a very important computational, a metric that is related to the computational complexity. And that is, in case of digital architectures, BY is the accumulator precision. And it has been actually found that even if you have networks that are binary networks or very low precision, hyper precision reduction has been applied. So let's say 3-bit weights or 2-bit weights, 1-bit activation, or vice versa, then you still have to do a long high dimensional dot products. And those dot products, the output of those dot products needs to be assigned a certain precision. And that output is the output of an accumulator. And so it just turns out that you end up with gigantic accumulators, even if the multiplies are low precision. Right, and so there's been a lot of work recently in figuring out, can I use a low complexity accumulator without compromising on the network accuracy? Okay, so that's for digital architectures. For in-memory architectures, actually BY turns out, BY is the precision of the output. It is actually directly equal to the ADC precision, the analog to digital converter that needs to be sort of retrofitted around the memory array. And since memory arrays are highly dense, it is very important that that precision be as small as possible. All right, and so reducing BY is very, very critical. Sometimes you don't give it much attention, maybe not for this community. All of you are probably paying a lot of attention to BY, but BY, which is the output precision. But we want to ask the question, what is the minimum value we can live with? So what is the metric we ought to be using in this kind of an analysis? We use a metric called signal-to-quantization noise ratio. It is a metric that is very commonly used in the design of fixed point digital signal processing systems, communication systems, and to some extent in some sophisticated DNN, fixed point DNN architecture design, SQNR is the metric that they use. So what is SQNR? It is based on this additive model of quantization noise. So you have a floating point input X, you quantize it to Bx bits, that introduces a noise Q sub X. And therefore, SQNR is simply the variance of X, the signal, to the variance of Q sub X, which is the noise, right? So that is SQNR. And it is possible to show, there's a very fundamental equation, again, many of you may already know this, that in dB, the signal to quantization noise ratio of one signal, one floating point signal, is given by 6 times Bx plus 4.78 minus the peak to average ratio of that signal X. And the peak to average ratio is simply the ratio of the peak value to the standard deviation of X. So average doesn't mean the mean of X, it just means, so it's really the peak to average power ratio, all right? So we just write it as the peak divided by the standard deviation. And you'll see here that this gives you a very nice rule of thumb that for every bit that you assign to X, you get a 6 dB gain in SQNR. So 6 dB per bit rule straight away emerges from this particular equation. So now let's step back and look at a dot product. So what happens in a dot product is you got quantization noise at the input, the weight has been quantized, inputs have been quantized, and at the output, you will get the impact of that quantization noise. So Q sub Iy is really the effect of quantization noise at the input, these two inputs, seen at the output. And in addition, we might decide to truncate or round off the output bits separately. And so that gives us an additional source of quantization noise, Q sub Y, okay? So at the end, what I would like is the total signal to quantization noise ratio should be the variance of this signal, the ideal floating point output, divided by the sum of the variances of these two noise components. And that has to be higher than certain lower bound that is imposed by network accuracy requirements. Okay, and to find that lower bound requires us to, that's the second topic of this talk in the outline, which is precision requirements for network accuracy. All right. So moving on then, the total SQNR that we see at the output that I just referred to is actually can be written down using this expression. And you'll see from this expression that if SQNR-Y, this is the signal to quantization noise ratio because of output quantization, this is only a function of BY. If it is sufficiently large than the input reflected quantization noise, then as the total SQNR is limited by only the first term, the SQNR QIY, right? The input quantization limits everything else. So for example, I might choose SQNR-Y to be, the second term here, to be 9 dB. I've just chosen this number, 9 dB greater than the input reflected noise. And if I do that, I can show that this total is within 0.5 dB of this upper bound. So SQNR QIY upper bounds the total SQNR, okay? And so, and that's captured in this equation here. If I increase BY, I can make SQNR, it's a free variable. BY is a free variable, so I can make it as large as I want. If I keep it fixed, then it drops with N. So as the dimensionality of the dot product increases, the signal to quantization noise ratio due to output quantization drops. So that forces me to say, well, let's make BY large to offset it. If I make it large, then it leads to large accumulator bit widths, and I run into the complexity problem. So question is, how do I choose BY? Okay. And the answer today, this is a very commonly used rule of criteria, is you assign BY to be simply, you let the bits grow, right? So BX plus BW, the input precisions, they go into a multiplier. Output precision is BX plus BW. You got to add N of those products to compute an N-dimensional dot product. And so you have BY given by this expression, fine. And so if I take this BY, plug it into the previous equation, I can show that this BGC or bit growth criteria will have the following expression in which both the SQNR and BY, they actually increase with the dot product dimension because there's a plus sign in both of these, and it's a monotonic function of n, right? So both of them increase with n. And so I'm safe. This is a very safe metric, safe method of achieving the maximum possible total SQNR at the output, because I can always make the output quantization noise small enough so that it's all, the total SQNR is totally dependent on the input quantization noise. Now, what we are proposing, we're going to claim that this is an overkill, right? This BGC is really an overkill. You should not do that. What is the alternative? The alternative is what we are proposing is a minimum precision criteria. In minimum precision criteria, the only difference is we allow a certain non-zero probability of clipping. So if that's the distribution of your output, okay, so density function of your output, that's your max and that's your min. And typically you'll spread the quantization levels between the min and the max, right? Here we say, don't do that. You actually allow for some clipping. You artificially impose a smaller max, y sub c, and then fit in your quantization levels in that regime, and let this clipping have a finite probability, finite but small probability of clipping. You permit that. And once we allow for that clipping probability, our equation changes. You know, it has a different form in which there are two terms. The first two terms are familiar. The last two terms, one is the peak to average ratio of the output. And the second term is sort of the additional correction factor due to clipping that we are permitting now. Now, these two terms actually trade off with each other. You know, if you allow for more clipping, you'll find that YC has to be reduced. Your quantization noise becomes less, clipping noise increases, and vice versa. So it's a very nice, beautiful trade-off. You can find the optimum setting so that SQNRY is maximized for the same number of bits BY. Right? And this trade-off is really important when your dimensionality increases. If your dot product dimensionality increases, then you'll see the distributions getting sharper and sort of peakier. And therefore, it doesn't make sense to actually spread out your quantization levels all the way from the true maximum to the true minimum. Instead, you just clip it and force fit the quantization levels in the sort of the informative part of the distribution. Okay. So this just compares what happens when we do when we use MPC and BGC. What do we end up with? This is for a x-axis here is the dimensionality of the dot product. The precision of x and y, I believe, are set to about 5 bits each. And now we are asking the question, what is the minimum output precision we need? The desired SQNRY is about 38.2. This is 9 dB above the input noise reflected at the output. And you'll see that BGC is sitting right up there. It's a real overkill because if you follow the bit growth model, you're giving that much margin when it is not needed. The MPC method is sitting right there with 8 bits. So this red curve is 8 bits. You meet the requirements on SQNR with 8 bits that BGC would be taking maybe 16 to 20 bits. All right. Now there's an alternative to BGC, which is sort of what we call a truncated BGC, where you simply drop so many LSBs. Now, if you went down to 8 bits with truncated BGC, it doesn't even meet the requirements. Okay. So what we are getting with MPC is something very different from bit growth model. And we believe this is the way to assign the minimum precision to meet a particular signal to quantization noise ratio at the output of the dot product. So this is at the dot product level. Okay, now the question would be, so that's the sort of the first part of my talk, and just wanted to see if any quick questions. I'm glad to answer. If not, okay. So yeah, so let's move on. So if you now know the output precision, BY, And we know that By is now totally a function of the input precisions, Bx and Bw, right? Because Bx and Bw introduce noise at the inputs that gets reflected to the output. And then we make sure the output precision is sufficiently high, not very high, but sufficiently high, so that the SQNR at the output is dominated by the quantization noise of weights and activations. So we know how to do that now. Now the big question is, how do I assign the precision of weights and activations? So that's what I mean by input precision requirements for DNN. And in other words, we are now not going to worry about B sub y. We'll just think about Bx and Bw. How do I find out the values of Bx and Bw so that a network accuracy is met? Okay, I'm now moving up to the network level. Now, this question has been looked at since 2015, when the first paper, that's the first paper I'm aware of, came from IBM. They were looking at training in fixed point. And since then, a number of papers, number of researchers have proposed low precision networks, low precision, particularly on the inference path, on the forward path. And if you read those papers, you'll find that it's almost like saying, I'm going to use 3 bits and see what happens. And I'm going to train it with 3 bits. And, SGD is sort of this grand old, grandfather algorithm, which is highly accommodating, kind, and gentle to all sorts of miscues and missteps made by designers, because you just do this global optimization and then try all sorts of learning rates and momentum and so on and so forth, and you get something that works. But there are no guarantees that it's going to work all the time, all right? So this is the sort of the state of the art as we look at it. And in this worldview, we are coming in and saying, look, let's do it. Let's talk about precision requirements with guarantees. And so there are these 3 pieces of work. Today, I'll just focus on the first 2, give you a high-level summary of what they mean. In the first work, this was published first in ICML 2017 and then in ICASP 2018. This is focusing on the inference path, saying, in the forward path, what is the minimum precision I should assign to weights and activation to achieve a certain level of accuracy? In last year's ICLR paper, we sort of extend this question to include backprop, the forward and backward path together. All right, so let's, and in both pieces of work, we are, in both pieces of work, we are using a framework in which we assume that there is a pre-trained floating point baseline. All right, so that's like a teacher. This floating point baseline is giving us the right accuracy. If it is for inference, I get very good classification error rate. I'm happy with this network, and everyone, most of the algorithm developers are working here. We say, okay, now you have this network. Can you please tell me, can you design a fixed point network and tell me what is the minimum activation precision and weight precision I should assign so that the mismatch between the output decision, the decisions made by the fixed point network and the floating point network, these decisions, the mismatch between them, that when they differ, when they disagree, that mismatch probability is less than a certain delta, right? Which what it means is it also means that when the floating point network makes an error, here we actually want the fixed point network to make the same error, right? So it's a little bit counterintuitive. We just want the fixed point network to track what the floating point network is doing, but it should be operating with finite precision or fixed point weights and activations. And so we have this bound, a very simple bound. So this whole analysis framework revolves around computing what are called as noise gains. So when I quantize the input activation, it creates this quantization noise. If you remember Q sub X, that Q is a random variable, so it has a variance. And the variance has to be propagated through the network, and that propagation path has a gain of E sub A, and same thing with the quantization noise for the weights. And so this upper bound on mismatch probability, P sub m, the probability that the two networks will disagree, is actually upper bounded by this expression, right? And so now, if I can calculate these two terms, the noise gains, maybe for every activation in the network, perhaps for every weight in the network, or maybe for every activation per layer, granularity of this analysis is up to me. I can plug it into this upper bound and sort of figure out how many bits I should put into the activation, how many into the weights, and then be able to ensure and guarantee that the mismatch will be less than a certain bound. So this is how we are framing this problem. So a few lessons we learned. One, yes, you can calculate the minimum precision requirements analytically. And if you look at the bound versus the actual precision from simulations, they're pretty much within 1 to 2 bits. All right. So in fact, the analysis is about 1 to 2 bits conservative compared to what the network actually needs. So that's good. You can do this offline and don't have to run long simulations to get this number. Second lesson is, if you look at the chart on the right, the precision of the weights and activation, they actually fall as the layer depth increases, which means the first layer will need more precision than the last layer. Why? Well, the reason for that is the noise gains in the first layer is higher than the noise gains in the last layer. All right, so you need to assign more bits to the weights and activations in layer 1 because it's going to be multiplied by a higher gain as it propagates to the output. All right, so that's the, and this is sort of confirmed by other researchers in the community using other methods. Lesson 3 is a bit counterintuitive. Binary nets, which everyone thinks is the ultimate in terms of complexity, we find that these minimum precision networks are in fact less complex than binary net, roughly about 3.5x in terms of computational complexity and 2x in terms of storage. And this is all obtained through this analysis, right? By doing this systematically and analytically. So that was about inference. Similar challenges are there when you bring in training. When it comes to training, not only do we have to worry about the forward path, but then we have to compute the cost function and propagate the gradients, both weight and activation gradients through the network all the way back down. And so there are a number of tensors whose precision has to be determined. For example, there's the weight gradient, there is the activation gradient, and then there is the weight accumulator. Those are 3 additional tensors whose precision has to be determined if we want to do fixed point training. And what makes fixed point training hard is, number one, the distribution I showed you earlier when we were discussing dot product. That distribution is not static, it is non-stationary, it changes over time. So both activation and weights have distributions that start off in one point in the first epoch and then keep changing their shape dramatically. Same thing with gradients. They have dynamic ranges that are widely different compared to the first epoch versus the last one. And the last problem here is that when you do the weight update in SGD-based methods, the weight gradient has to be added to the weights, and there's a big mismatch between the dynamic range of the weights in the weight accumulator and the dynamic range of the weight gradients, right? So it's a large number versus a very small number being added together. So how do we manage these challenges? Well, I won't go through all the criteria here, but you can see some semblance of formulas we've seen earlier. We have 5 different criteria meant to ensure that if I take a fixed point network and train it from scratch, then its convergence behavior will be with very high fidelity, close to that of the floating point network. This is the guarantee that we are giving if these 5 criteria are satisfied. Okay. So here is one example of this of the results of this work. You can see, I'll just look at, if you look at the left-hand side graph, there's a loss on the left y-axis and the test error rate on the right y-axis. And you'll see that the convergence curves, the floating point convergence curve is in black. And there are three possible curves, one in blue, red, and green. C naught is what the analysis tells us it should be. C plus and C minus says, okay, I'm going to just increase all the precisions by 1 bit and then run it again and reduce the precisions by 1 bit and run it again from C naught. So C naught is the assigned precision, the so-called close to optimal precision. And we find that if you increase the precision by 1 bit, you don't get too much benefit. You reduce precision by 1 bit, there's a huge change. You can see a discernible change in both the loss as well as the accuracy. All right, so this tells us that the precision assignment is indeed a good one, and that you can come to it without having to search over a very, very complicated, very, very complex search space, right? We have so many network parameters, and each one has can be assigned a unique precision. That search space is very hard to navigate, but these kind of theoretical insights do help us. Then, of course, the per layer precision trends can also be talked about. Weight precision decreases from input to the output. We saw that earlier. The precision of gradients, activation gradients, and weight accumulators, they increase from the input to the output. So that's an opposite trend to what we would see for weights and activations in the forward path. In the reverse path, we see a reverse, an opposite trend. And then finally, this chart just shows the cost. When you apply those precision requirements, the precision assignments, you can see that there is a big savings in the storage requirements of the weight parameters. There's this column, activation parameters, computational cost of both forward and backward path. And then this is the cost of communicating the gradients during training. So there are many, for distributed training frameworks, the cost of communicating gradients becomes important. And this column shows you the savings that we get when we use our fixed point method. And so, for binarization and ternarization, these are very aggressive techniques for reducing precision. You typically have a loss in accuracy, which is hard to overcome. And these are not actually, these binarized networks are many times trained with full precision backprop. Whereas FX, the one that I'm talking about, it's fixed point in both the forward and the backward path. All right, so that was my second topic. The last one will be a short one, so I just want to see if any thoughts here. If not, then the last part is the big question in front of some of us here, which is what are the precision requirements of this in-memory architectures? What are those? Actually, they are very interesting set of architectures where you just eliminate the von Neumann memory wall problem by embedding computations in the periphery of the memory array. Now, traditionally, you cannot do that because it makes computations to occur in analog, and who wants analog computation with all the attendant problems? But with machine learning methods, we are desperate. We want to reduce energy cost. We want to enhance the latency, reduce the latency. And so people are aggressively pursuing these methods. And our group actually proposed this idea for the first time in 2014. And then we have come out with a number of chips in 65 nanometer process and shown pretty dramatic gains, that is reductions in energy delay product over an equivalent von Neumann architecture. And so it has created, this line of work has created a lot of splash in the sort of circuit / architecture communities. Just recently this year, We published the first book on deep in-memory architectures that's out there. And if you look at the integrated circuit design, the semiconductor community, lots of designers and researchers are now building in-memory architectures, and and all of them are showing these big gains in energy latency product. But this big question no one has really been able to answer is, what are the precision limits? Meaning, when I compute in analog, I get energy latency benefits, but can I compute accurately, right? And what are the limits? What limits this the computational accuracy? And so we try to answer this question in our work, since we have a good understanding of what the precision requirements are. So we bring that knowledge to the problem of in-memory computing. And so this is sort of the bit cell array. You have quantized inputs, quantized weights, and you have an analog output, which then is quantized by the ADC to generate the output, Y. Okay, so very similar to the dot product problem. In fact, the only new terms that show up are these two terms, the eta terms, which are analog sort of artifacts. One is the analog spatiotemporal variations that occur in an SRAM array that creates variations in the discharge currents and therefore variations in the bit line voltages. And then clipping, all of these bit lines have a limited supply voltage, so they can clip. And so those are two new terms that appear, and now we have to accommodate those. And the story is exactly the same. We were delighted to see that the total SNR, here we are using SNR instead of SQNR, because here we have not only quantization noise, but also these analog circuit noise contributors. So just to be fair, we say it's SNR, and it has the similar form. There's an analog SNR, there's a digital quantization SNR, and we want digital quantization SNR to be larger, significantly larger than the analog SNR. And so we are also limited by SNR-A. Fundamentally, before you reach the A to D converter, whatever happens in the memory core is your true limiter of accuracy of in-memory computing. And we can, in fact, obtain expressions for analog SNR and show that there is a trade-off between clipping noise, the headroom clipping noise, and the circuit noise. And so this graph here shows that as the dimensionality of the dot product increases, initially the SNR-A, which is roughly a little bit below 20 dB, it is totally because there's a lot of variations in the bit cell currents. But as soon as you increase N, the dimensionality, there are a lot more currents being added up, a lot of charge being taken out of the bit lines. And so you start clipping, and that part is your clipping noise. All right, so there's a trade-off between the two. And keeping that trade-off in mind, we can find a lower bound on the precision of the A to D converter. And this gives us an exact expression for finding those optimal values for BY, the ADC precision, so that the total SNR is close to SNR-A. If you draw a horizontal line slightly less than 20 dB, that is the analog SNR upper bound that was established in the previous slide. So again, all of these different components are coming together well, connecting well. Let me now just quickly summarize. The points I want to make here is that design of fixed point DNNs or finite precision DNNs, in fact, design of DNNs need not be based on trial and error. For precision assignment, at least, we have analytical methods to find those. Talked about minimum precision criteria and noise gain analysis that helps us figure out for what the minimum precision requirements are for DNNs. Using those analysis methods, we can also find the precision requirements for in-memory architectures. So all of these techniques are sitting out there. Maybe sometimes I wonder if we should have a design optimization framework in which network accuracy, energy, and latency, they're all sort of traded off systematically with each other. All right, it's feasible. And finally, this is just me sort of looking at the world around us and, saying, why can't we build AI systems like we build engineered systems, where you have a system requirement, you say, well, from the system requirements, I got this component level metrics. Let me now build a component that meets those specifications, then compose a large scale AI system, and I can now give guarantees on the behavior of that particular intelligent machine, right? So this sort of an engineered design of AI systems, designed with guarantees. These are very challenging problems in front of us. And I think it requires everybody from different communities to come together, exchange ideas and share thoughts, to build systems that people can trust, that society can trust. So with that, I thank you all for attending, listening to me, and I'm open to any questions that anyone might have. So thank you.